In mathematics, Clifford algebras are a type of associative algebra. As K-algebras, they generalize the real numbers, complex numbers, quaternions, and several other hypercomplex number systems. The theory of Clifford algebras is intimately connected with the theory of quadratic forms and orthogonal transformations. Clifford algebras have important applications in a variety of fields including geometry, theoretical physics and digital image processing. They are named after the English geometer William Kingdon Clifford. The most familiar Clifford algebra, or orthogonal Clifford algebra, is also referred to as Riemannian Clifford algebra. Introduction and basic properties. A Clifford algebra is a unital associative algebra that contains and is generated by a vector space V over a field K, where V is equipped with a quadratic form Q. The Clifford algebra.As is the freest algebra generated by V subject to the condition where the product on the left is that of the algebra, and the 1 is its multiplicative identity. The definition of a Clifford algebra endows the algebra with more structure than a bare K-algebra. Specifically, it has a designated or privileged subspace V. Such a subspace cannot in general be uniquely determined given only a K-algebra isomorphic to the Clifford algebra. If the characteristic of the ground field K is not 2, then one can rewrite this fundamental identity in the form whereas the symmetric bilinear form associated with Q, via the polarization identity. The idea of being the freest, or most general, algebra subject to this identity can be formally expressed through the notion of a universal property, as done below. Quadratic forms and Clifford algebras in characteristic 2 form an exceptional case. In particular, if char equals 2, it is not true that a quadratic form determines a symmetric bilinear form, or that every quadratic form admits an orthogonal basis. Many of the statements in this article include the condition that the characteristic is not 2, and are false if this condition is removed. As a quantization of the exterior algebra, Clifford algebras are closely related to exterior algebras. In fact, if Q equals 0, then the Clifford algebra.As is just the exterior algebra lambda. For non-zero Q, there exists a canonical linear isomorphism between lambda and C whenever the ground field K does not have characteristic 2. That is, they are naturally isomorphic as vector spaces, but with different multiplications. Clifford multiplication together with the privileged subspace is strictly richer than the exterior product since it makes use of the extra information provided by Q. More precisely, Clifford algebras may be thought of as quantizations of the exterior algebra, in the same way that the Weyl algebra is a quantization of the symmetric algebra. Weyl algebras and Clifford algebras admit a further structure of her asterisk algebra, and can be unified as even and odd terms of a superalgebra, as discussed in CCR and CAR algebras. Universal property and construction. Let V be a vector space over a field K, and let Q, Vk be a quadratic form on V. In most cases of interest, the field K is either the field of real numbers R, or the field of complex numbers C, or a finite field. A Clifford algebra.As is a unital associative algebra over K together with a linear map I, Vc satisfying I2 equals Q1 for all Vv, defined by the following universal property. Given any associative algebra A over K and any linear map J, Va such that J2 equals Q1A for all Vv, there is a unique algebra homomorphism F. Ca such that the following diagram commutes, working with a symmetric bilinear form less than, greater than instead of Q. The requirement on J is a Clifford algebra as described above always exists and can be constructed as follows. Start with the most general algebra that contains V, namely the tensor algebra T, and then enforce the fundamental identity by taking a suitable quotient. In our case, we want to take the two-sided ideal IQ generated by all elements of the form for all and define C as the quotient algebra C equals T IQ. The ring products inherited by this quotient is sometimes referred to as the Clifford product to differentiate it from the exterior product and the scalar product. It is then straightforward to show that C contains V and satisfies the above universal property, so that C is unique up to a unique isomorphism. Thus one speaks of the Clifford algebra C. It also follows from this construction that I is injective. One usually drops the I and considers V as a linear subspace of C. The universal characterization of the Clifford algebra shows that the construction of C is functorial in nature. Namely, C can be considered as a functor from the category of vector spaces with quadratic forms to the category of associative algebras. The universal property guarantees that linear maps between vector spaces extend uniquely to algebra homomorphisms between the associated Clifford algebras, basis and dimension. If the dimension of E over K is n and E1, n is an orthogonal basis of, then C is free over K with a basis. The empty product is defined as the multiplicative identity element. For each value of K there are n choose K basis elements. So the total dimension of the Clifford algebra is, since V comes equipped with a quadratic form, there is a set of privileged bases for V, the orthogonal ones. An orthogonal basis is one such that for, and where is the symmetric bilinear form associated to Q. The fundamental Clifford identity implies that for an orthogonal basis for, and this makes manipulation of orthogonal basis vectors quite simple. Given a product of distinct orthogonal basis vectors of E, one can put them into standard order while including an overall sign determined by the number of pairwise swaps needed to do so. Examples: real and complex Clifford algebras. The most important Clifford algebras are those over real and complex vector spaces equipped with non-degenerate quadratic forms. It turns out that every one of the algebras CP, Q and Cn is isomorphic to A or AA, where A is a full matrix ring with entries from R, C, or H. For a complete classification of these algebras, see classification of Clifford algebras. Real numbers. The geometric interpretation of real Clifford algebras is known as geometric algebra. Every non-degenerate quadratic form on a finite-dimensional real vector space is equivalent to the standard diagonal form, where n equals p plus q is the dimension of the vector space. The pair of integers is called the signature of the quadratic form. The real vector space with this quadratic form is often denoted Rp. The Clifford algebra on Rpq is denoted Cp. The symbol Cn means either Cn, 0 or C0, and depending on whether the author prefers positive definite or negative definite spaces. A standard orthonormal basis, A, for Rp, Q consists of n equals p plus q mutually orthogonal vectors, p of which have norm plus 1 and q of which have norm minus 1. The algebra Cp, Q will therefore have p vectors that square to plus 1 and q vectors that square to minus 1. Note that C0, 0 is naturally isomorphic to R since there are no non-zero vectors. C0, 1 is a two-dimensional algebra generated by a single vector E1 that squares to minus 1, and therefore is isomorphic to C. The field of complex numbers. The algebra C0, 2 is a four-dimensional algebra spanned by 1, E1, E2, E1, E2. The latter three elements square to minus 1 and all anti-commute, and so the algebra is isomorphic to the Quaternions H. C0, 3 is an 8-dimensional algebra isomorphic to the direct sum HH called split biquaternions. Complex numbers. One can also study Clifford algebras on complex vector spaces. Every non-degenerate quadratic form on a complex vector space is equivalent to the standard diagonal form where n equals dim v, up to isomorphism, so there is only one non-degenerate Clifford algebra for each dimension n. We will denote the Clifford algebra on Cn with the standard quadratic form by Cn. The first few cases are not hard to compute. One finds that C0C, the complex numbers C1 CC, the bicomplex numbers C2M, the bit Quaternions where M denotes the algebra of n times n matrices over C. Examples: constructing quaternions and dual quaternions. Quaternions in this section. Hamilton's quaternions are constructed as the even subalgebra of the Clifford algebra C0, 3. Let the vector space V be real three-dimensional space R3, and the quadratic form Q be derived from the usual Euclidean metric. Then, for V, W in R3 we have the quadratic form, or scalar product. Now introduce the Clifford product of vectors V and W given by this formulation uses the negative sign, so the correspondence with quaternions is easily shown. Denote a set of orthogonal unit vectors of R3 as E1, E2, and E3. Then the Clifford product yields the relations, and the general element of the Clifford algebra C0, 3 is given by the linear combination of the even grade elements of C0, 3 defines the even subalgebra C00, 3 with the general element. The basis elements can be identified with the quaternion basis elements I, J, K as, which shows that the even subalgebra C00, 3 is Hamilton's real quaternion algebra. To see this, compute and finally, dual quaternions in this section. Dual quaternions are constructed as the even Clifford algebra of real four-dimensional space with a degenerate quadratic form. Let the vector space V be real four-dimensional space R4, and let the quadratic form Q be a degenerate form derived from the Euclidean metric on R3. For V, W in R4 introduce the degenerate bilinear form. This degenerate scalar product projects distance measurements in R4 onto the R3 hyperplane. The Clifford product of vectors V and W is given by note. The negative sign is introduced to simplify the correspondence with quaternions. Denote a set of orthogonal unit vectors of R4 as E1, E2, E3 and E4. Then the Clifford product yields the relations, and the general element of the Clifford algebra C has 16 components. The linear combination of the even-graded elements defines the even subalgebra C0 with the general element. The basis elements can be identified with the quaternion basis elements I, J, K and the dual unit epsilon, as this provides the correspondence of C00, 3, 1 with dual quaternion algebra. To see this, compute and the exchanges of E1 and E4 alternate signs an even number of times, and show the dual unit epsilon commutes with the quaternion basis elements I, J, and K. Examples: in small dimension, let K be any field of characteristic not 2. Rank 1 if Q has diagonalization A, that is, there is a non-zero vector X such that Q equals A. Then C is a K-algebra generated by an element X satisfying X2 equals A, so it is the at-Al quadratic algebra K, X. In particular, if A equals 0, then C is the dual numbers algebra over K. If A is a non-zero square in K, then C equals K times K. Otherwise, C is the quadratic field extension K of K. Thus C is the quaternion algebra K. We retrieve the real case when A equals B equals -1, since A equals R. As a special case, if some X in V satisfies Q equals 1, then C equals M2. Properties. Relation to the exterior algebra. Given a vector space V1 can construct the exterior algebra lambda, whose definition is independent of any quadratic form on V. It turns out that if K does not have characteristic 2, then there is a natural isomorphism between lambda and C considered as vector spaces. This is an algebra isomorphism if and only if Q equals 0. One can thus consider the Clifford algebra C as an enrichment of the exterior algebra on V with the multiplication that depends on Q. The easiest way to establish the isomorphism is to choose an orthogonal basis A for V and extend it to a basis for C as described above. The map C lambda is determined by note that this only works if the basis A is orthogonal. One can show that this map is independent of the choice of orthogonal basis and so gives a natural isomorphism. If the characteristic of K is 0, one can also establish the isomorphism by anti-symmetrizing. Define functions fk, v times vc by where the sum is taken over the symmetric group on K elements. Since fk is alternating, it induces a unique linear map lambda kc. The direct sum of these maps gives a linear map between lambda and C. This map can be shown to be a linear isomorphism, and it is natural. A more sophisticated way to view the relationship is to construct a filtration on C. Recall that the tensor algebra T has a natural filtration, F0, F1, F2, where Fk contains sums of tensors with order k. Projecting this down to the Clifford algebra gives a filtration on C. The associated graded algebra is naturally isomorphic to the exterior algebra lambda. Since the associated graded algebra of a filtered algebra is always isomorphic to the filtered algebra as filtered vector spaces, this provides an isomorphism in any characteristic, even 2. Grading in the following. Assume that the characteristic is not 2. Clifford algebras is Z2 graded algebras. Indeed, the linear map on V defined by V minus V preserves the quadratic form Q, and so by the universal property of Clifford algebras extends to an algebra. Automorphism alpha, CC. Since alpha is an involution, one can decompose C into positive and negative eigenspaces of alpha where Ci equals xc, alpha equals x. Since alpha is an automorphism, it follows that where the superscripts are read modulo 2. This gives C the structure of a Z2 graded algebra. The subspace C0 forms a subalgebra of C, called the even subalgebra. The subspace C1 is called the odd part of C. This Z2 grading plays an important role in the analysis and application of Clifford algebras. The automorphism alpha is called the main involution or grade involution. Elements that appear in this Z2 grading are simply said to be even or odd. Remark. In characteristic knots 2, the underlying vector space of C inherits an N grading and AZ grading from the canonical isomorphism with the underlying vector space of the exterior algebra lambda. It is important to note, however, that this is a vector space grading only. That is, Clifford multiplication does not respect the N grading or Z grading, only the Z2 grading. For instance, if Q0, then VC1, but V2C0, not in C2. Happily, the gradings are related in the natural way. Z2N, 2N, Z2Z. Further, the Clifford algebra is Z-filtered. Ci plus J. The degree of a Clifford number usually refers to the degree in the N grading. The even subalgebra C0 of a Clifford algebra is itself isomorphic to a Clifford algebra. If V is the orthogonal direct sum of a vector of non-zero norm Q in a subspace U, then C0 is isomorphic to CQ, where minus QQ is the form Q restricted to U and multiplied by minus Q. In particular, over the rails, this implies that for Q greater than 0, and for P greater than 0. In the negative definite case, this gives an inclusion C0 n minus 1 C0 n, which extends the sequence RCHHH. Likewise, in the complex case, one can show that the even subalgebra of Cn is isomorphic to Cn-1. Anti-automorphisms. In addition to the automorphism alpha, there are two anti-automorphisms which play an important role in the analysis of Clifford algebras. Recall that the tensor algebra T comes with an anti-automorphism that reverses the order in all products. Since the ideal IQ is invariant under this reversal, this operation descends to an anti-automorphism of C called the transpose or reversal operation, denoted by xt. The transpose is an anti-automorphism, T equals ytxt. The transpose operation makes no use of the Z2 grading, so we define a second anti-automorphism by composing alpha and the transpose. We call this operation Clifford conjugation, denoted of the two anti-automorphisms. The transpose is the more fundamental. Note that all of these operations are involutions. One can show that they act as plus or minus 1 on elements which appear in the Z grading. In fact, all three operations depend only on the degree modulo 4. That is, if X is pure with degree K, then where the signs are given by the following table. Clifford scalar product when the characteristic is not 2. The quadratic form Q on V can be extended to a quadratic form on all of C. A basis-independent definition of one such extension is where it denotes the scalar part of A. One can show that where the V are elements of V, this identity is not true for arbitrary elements of C. The associated symmetric bilinear form on C is given by one can check that this reduces to the original bilinear form when restricted to V. The bilinear form on all of C is non-degenerate if and only if it is non-degenerate on V. It is not hard to verify that the transpose is the adjoint of left-right Clifford multiplication with respect to this inner product.